first virtual seminar this semester. We'll have a bunch more talks. Some are already announced on the website. And we're very pleased to kick off the seminar with a talk by Dennis Stanton from Minnesota, University of Minnesota. And he's going to be talking about some historical remarks and recent conjectures for integer partitions.
Thank you very much for the introduction, Larry, and thanks to you and Ian for inviting me to give this talk. Before I launch into the talk, a few words of wisdoms for any graduate students there. It's a little strange that I'm talking about integer partitions, even though I never ever took any course in number theory or combinatorics, either as an undergraduate or a graduate student. So this means you never quite know where your life will lead as a graduate student. So think positive. You just never know. Okay, here's the outline. I'm going to have two main topics. First, I'm going to talk about the Ramanujan congruences for the partition function P of n, the number of integer partitions of n, and the combinatorial versions of those from ranks and cranks. And then I'll say some things about Rogers-Ramanujan identities and refinements of them. So this talk has basically two parts. Okay, let's start on the first part. The Ramanujan congruences for P of n. So here we have these three congruences for P of n. This is for mod 5, mod 7, and mod 11. And there are versions for mod powers of 5, powers of 7, and powers of 11, but I won't talk about that at all. And the concentration of this talk will be about a combinatorial proof of these congruences. Namely, what you'd like to do is to split the partitions of 5n plus 4 into 5 equal classes. That's what you'd like to do. And then what you'd like to do is to give explicit bijections between those 5 classes. You'd like to do that for 5, for 7, and for 11. That's the main goal. Any questions about the main goal? So here's some historical information about how that has been done. For 5 and 7, this was done by Dyson. He invented this statistic called Dyson's rank in 1944. Given a partition lambda, the rank is the largest part minus the number of parts. So here I have this Ferris diagram of the partition 4, 3, 1. The largest part is 4, the number of parts is 3, the rank is equal to 1. So he conjectured that the rank modulo 5 would split up the partitions into 5 equal classes. And it would also work for modulo 7. If you take the rank modulo 7, it would split into 7 equal classes and prove those conjectures. And it took 10 years before this was proven by Atkin and Swinnerton and Dyer, and they used those Heck-out operators to prove that. But 11 was missing. This Dyson's rank does not work for mod 11. So Dyson hypothesized a statistic called crank that would work for 11. And finally, a crank was found in 1987 by Frank Garvin and George Andrews. And here is what their crank was. I'm going to call it the AG crank, Andrews-Garvin crank. Their crank depended upon how many ones you had in the partition. If you had no ones, it was the largest part lambda 1. If you did have some ones, then it was the number of parts which are greater than the number of ones minus the number of ones. So this looks very strange. A number of parts greater than the number of ones minus the number of ones. And they proved that this AG crank worked for 5, 7, and 11. Now, neither of these statistics, Dyson's rank or the Andrews-Garvin crank, had or even have today a bijective proof. Nobody knows how to give bijections between the rank classes or the crank classes. That's still an open problem. We cannot do that. Fortunately, there's another kind of crank for which we can do that, a different crank. So this is called the 5-core crank, and this was done by Frank Garvin, Dong-Soo Kim, and I in 1990. So this method of computing a statistic involves something called 5 cores of partitions. So here I have a partition on the screen 5421 with this Ferris diagram. And you'll notice I've written in numbers along the diagonal. The main diagonal are all zeros. The upper diagonal is 1, 2s, 3s, 4s. Then you would go back to zeros. You put in these numbers modulo 5 in these boxes. And you count how many zeros there are. There's 2 zeros, so R sub 0 is 2. How many 1s there are, how many 2s there are, how many 3s there are, and how many 4s there are. And you form this linear combination of these R numbers. R1 plus 2R2 minus 2R3 minus R4. That's the 5-core crank. And what you do in general is to take a partition lambda, you find its 5-core. In this case, the 5-core of this exact lambda is lambda itself. The 5-core is what you get by stripping away all hooks that are multiples of 5. So none of the hooks in this partition have any multiples of 5. Like this hook right here of the second 0 is size 4. This hook with this 2 is a 4. This hook with this 1 is a 6. No hook is a multiple of 5. That makes it a 5-core. So the statistic is take lambda, take its 5-core, compute this combination of the R's, reduce it modulo 5. That's another crank statistic, which will prove Ramanujan's congruence. And you can also do this for mod 7 and mod 11. You do exactly the same thing. You take the 7-core, you compute these 7 numbers, and you form a different linear combination and reduce it modulo 7. And that is a crank that works modulo 7 and also modulo 11. Any questions about these 2 cranks and 1 rank, which all prove Ramanujan congruences? Here's a little table. Here I've listed the partitions of 4. There's 5 of them. So for example, this 2, 1, 1. Rank is largest part minus number of parts. Rank would be equal to 1. Notice these rank numbers, when I reduce modulo 5, I get 0, 1, 2, 3, and 4. Every number modulo 5 shows up. Same thing over here, 0, 1, 2, 1, 2, 3, and 4. And the 5-core crank also. They have here these generating functions. I'm going to call this rank sub 4 is the generating function of the rank. Just take z raised to these powers. The generating function with the AG crank, take z raised to these powers, and the 5-core crank is z raised to these powers. These are these polynomials, these 3 different generating functions. So we could do it in general. I call it rank sub n for partitions of n, AG crank, and 5-core crank for these 5 different polynomials, 3 different polynomials. One thing that we know are generating functions for these polynomials. For the rank, it only depends upon the largest part and the number of parts. So we can reduce the Durfee square out and get this generating function very easily. For the crank, it's not too obvious that this generating function factors into an infinite product. In fact, it's not true of n equals 1. N equals 1 is special. It's not true of q to the first. For example, the coefficient of q in this, you get a -1 from the top and a z plus 1 over z. You'd have z plus 1 over z minus 1, 3 terms. There's only one partition of 1, which is not true. But we're not too worried about it being wrong at 1. We can deal with that. And the way Andrews and Garvin figured this out is they started with this generating function, which they knew was a good one. They knew it was good because they knew if you put z to be a fifth root of unity and took all the coefficients of q to the 5n plus 4, you got 0. So they reduced that crank condition to a condition about this generating function being 0 when z was a fifth root of unity. So basically what they were able to do was do some manipulations on this infinite product and interpret it all positively. It's not at all clear that all the coefficients are positive here, but that's what they did. And so they got this interpretation for this crank, and that's where their statistic came from. For the 5-core crank, something a little more complicated is true, but actually it's better than the other generating functions, in my opinion. What's more complicated is, if I were just to do the 5-core crank at n, I could tell you what that is, but I'm not going to tell you. I'm going to tell you what it is on 5n plus 4. I'm going to restrict it to 5n plus 4. Then it turns out there's some infinite products out in front, and it's the generating function for a certain quadratic form, this q of a. And what makes this quadratic form very nice is it's basically the weight function of a 5-gon. There's 5-fold symmetry, obvious in this quadratic form. There's a 5-cycle that will act and preserve this quadratic form. That 5-cycle looks like it should be exactly the 5-cycle we want that proves the bijection on the 5-core crank classes, and it is. All you need to do is to check that there are no fixed points under the 5-cycle, just permuting the A's, cyclically permuting the A's. Well, if you're fixed under cyclic permutations, all the A's would be the same, and then you wouldn't get A dot 1 equals 1. A is an integer. That just can't happen. So there are no fixed points. So for the 5-core crank, because it's the generating function of a quadratic form, you immediately get bijections for the 5-core crank classes. That comes out for free, which does not come out of these other generating functions. So the lesson here is a more complicated generating function, revealing symmetry. And that's what we were looking for. Just for fun, I made a little table here of the other symmetry groups for other congruence classes. So these blue ones, 5m plus 4, it's the dihedral group of order 10 that acts on a pentagon. And for 7n plus 5, it's the dihedral group of order 14 that acts on a 7-gon. Those are the Vermontergen congruences. There's always at least a Z2, which comes from taking conjugate. Conjugation is going to preserve this business of being a T-core. Look at some of these other symmetry groups, though. These other dihedral groups for 5 and these other dihedral groups for 7. You know, Frank and I found these groups in the late 1980s when we took over all of the Apollo workstations of the IMA. We crept onto all these machines and ran some programs for 2 or 3 weeks to search out all possible symmetries of that quadratic form. And this is the results that we found. I'd like to know, is there some a priori reason for these groups? Are these symmetry groups related in any way to something else that you could immediately write down the answer? I don't know the answer to that. I'd really like to see such an answer. And we couldn't do things like 25, 125. We don't know what those groups are. I can't tell you that the group for 25 is a dihedral group of order 50. That I don't know. So for the higher Ramanujan congruences, what are these symmetry groups? So I'd really like to see an answer to this. You can find this table in this paper I did with Frank. Around 1990 in Mathematics of Computation.
I think we might, Nicholas, do you have a question?
Just a casual observation. I don't know if this is what you're looking for exactly, but I'm looking at these symmetry groups. Take, for example, 7n plus, say, 1, 3, and 4.
Yes?
You have D6, right?
Yes.
So it turns out there is an identity, a Kohlberg-style identity for the generating functions of P of 7n plus 1, 3, and 4. And it's those specific series multiplied together on the left-hand side. And it's a similar thing for 7n, 7n plus 2, and 7n plus 6. And then 7n plus 5 is by itself as a standard Ramanujan identity. So it's neat to just point that out. This could be related to the orbits that you get in the Ramanujan-Kohlberg identities.
It could be, yes. I will talk about the Ramanujan identity quite soon. So you may be right about that, that the fact that those symmetry groups are the same or related to these identities. You can figure out what those orbits are going to be. That I don't know. Now, Frank and I tried some things like that in that paper, but I don't think we went up to 7. I think we stayed over here in the lower cases. So now I am going to talk about this, what Hardy called Ramanujan's most beautiful formula. So here's Ramanujan's amazing formula for the generating function for P of 5n plus 4. 5 times a quotient of infinite products. This is most beautiful Ramanujan formula. I'm going to show you a combinatorial proof of this. So I actually have been to talks by some of my colleagues who said there's no combinatorial proof of this. That's false. It comes from our paper with Frank and Dong-Soo Kim. So here's the proof. First thing you do is you take all partitions and you decompose them into their quotients and their 5 cores. That turns into this identity, which is the generating function for 5 cores. A5 of n is 5 cores. So now, just take the 5n plus 4 part of that. Well, that means you must have only these terms that are 4 mod 5. These things only give you 0 mod 5. So you restrict. But we know that the 5 cores satisfy this amazing fact. A5 of 5n plus 4 of 5 A5 of n. And in fact, there's a bijection for that. Given a 5 core of n, I can produce 5 cores of 5n plus 4. There's an explicit map that does this. We just put that in, put the generating function back in, and we're done. So this Ramanujan formula comes very nicely from the 5 core generating function. Now for 7 cores, it's a more complicated formula. This formula 7n plus 5, there's 2 terms, 2 infinite products here. It's not nearly as nice. Okay, is there a combinatorial reduction for these rank polynomials and crank polynomials? Is it true that when I put in a z, instead of getting a 5, I get this polynomial in z times something that's positive? I know I have to get this polynomial in z because if z is the 5th root of unity, I get 0. That's a factor. This is the irreducible polynomial. And the answer is no. Look at this. Even for rank 4, when I factor this, I get some negative coefficients here. It didn't work. Okay, so either we quit or we try something different. So here we're going to try something different. I'm going to try something called the modified rank. The modified rank is take the rank and change only 2 terms of it. Change 2 terms which correspond to 2 partitions, either n or 1 to the n. Here the rank would be n minus 1. I'm going to replace it by n minus 2. And 1 to the n, I'll replace 1 minus n by 2 minus n. I'll just change those 2 partitions and define this modified rank. And then it seems like it's true. If I take the modified rank, and it does factor with this z version of 5 times a positive polynomial. And it also works for 7. So this would say, with this modified rank, there's some combinatorial decomposition of an integer partition into something like a 5 cycle and something else. There should be some 5 cycle symmetry going on with this modified rank instead of the normal rank. And I'm saying that that's why we haven't been able to do it with the normal rank. It was slightly off, that this is a better statistic to have. So I want to thank Frank, who has verified these 2 conjectures up to about 1,000. What about cranks? Do cranks factor, those crank polynomials? Well, it turns out Ramanujan was very interested in this, and his lost notebook actually had these calculations in it. Here is a paper of Bruce Berendt, H.H. Chan, S.H. Chan, and Wen-Chi Liao that talks about this, that this may have been one of the last things that Ramanujan worked on. It was on page 181 of his lost notebooks. And here are some things that are out of it. Here he's factoring these crank polynomials. Somehow he knew about the crank as a generating function, because he knew if you put z equal 1, that 1 infinite product over 2 infinite products become just the partition generating function. So it's not so unnatural to take that as a, that's what he did. He started factoring it, and notice, P of 4, there's a row 5. P of 9 has a row 5. P of 14 has a row 5. That's the 5. So there's the 5 that he has. There's his row 5. And here's his other stuff. What Ramanujan didn't notice is the other stuff, actually, if you didn't factor it, it was all positive. He was very interested in factoring it to get the congruence. So looks like this conjecture is true. If you take the AG crank of 5n plus 4 and divide by this polynomial, you get a positive polynomial. I couldn't find such a theorem for 7 or 11, though. Couldn't find that. So it made up this modified AG crank. Again, you changed the definition on 2 partitions. And this modified version seems to work for 5, 7, and 11. Frank checked that up to 1,000, and fortunately today, I can tell you this is true. Catherine Brigman, Ken Ono, Larry Olin, Ian Wagner, and Tripp. What's Tripp's first name?
Zach.
Zach Tripp. Now, I don't know if you did this year or last year, but apparently you've proven these conjectures. Is that correct, Larry?
Yeah, that's right. I guess
Well,
last year.
Positive, but you haven't found what this 5 cycle, 7 cycle, or 11 cycle is yet.
No, that's right.
What about the 5 core? Well, for the 5 core, similar theorem holds without any modification. It seems that if you divide by this version of 5, it is a positive polynomial. And then there's a restriction to something called the BG crank. It's due to Alex Berkovich and Frank Garvin. That also works too. And I've been told by Larry that that's now a theorem. Is correct, Larry?
Well, we haven't proven it for that case, but we have some observations about what might be special about the 5 core crank and why it works right away and the 7 and the 11 don't work the same.
Yes.
But we didn't actually show the positivity conjecture in this case.
Okay. Notice I didn't know what was happening at 7 and 11 because I couldn't get it to work. So you have some information about why that might be true.
Mm-hmm.
Okay, so I won't call this a theorem. I will just call it a work in progress now.
Sure. Yeah.
How about some other cranks? In this talk so far, I've had 1 rank and 2 cranks. Here's a different AG crank. So I came up with this last summer while I was thinking about cranks. Instead of having just 1s, I'm going to be interested in 1s and 2s. Take the number of 1s, S, the number of 2s, T, and now instead of taking parts which are greater than the number of 1s, I want to take the number of parts which are greater than the number of 1s plus number of 2s plus 1. Then here's another crank statistic. If there are no 1s and 2s, it's the largest part. If there's 1, 1 and no 2s, it's the largest part minus 1. If there's a 2 and no 1s, then it's the second largest part minus 1. Otherwise, it's this funny combination of U, S, and T. So the theorem is that this also proves the Ramanujan congruences mod 5, 7, and 11. The only reason is this has the same identical generating function as the AG crank. And in fact, that's how you prove this. You take the AG crank generating function and you massage it in a certain way that proves positivity using more terms than what George and Frank did. They split off 1 term from the Q binomial theorem. I split off 2 terms and do some manipulations to get everything else positive, and then reinterpret all these things combinatorially. So this is kind of an icky thing, I have to admit. But I did it because I was wondering, what if I did instead of 1, 1, 2, 1, 2, 3, I went up to 5. Maybe I had some 5 cycle there. I decided that maybe I could do 3, but it's going to be pretty complicated for 1s, 2s, and 3s. And to go up to 5 would be beyond what I'd ever want to do. So I kind of gave up on this. But more can be done with this AG crank. Here's another thing called the MEX. Oh, this is something that I recently did with Brian Hopkins and James Sellers. Here's the definition of the MEX. Take a partition lambda and J some part of lambda. MEX sub J of lambda is the smallest integer bigger than J, which is not in lambda. So if J plus 1 is not in lambda, it's J plus 1. And then here's a way of changing crank statistics into mech statistics, this theorem. Crank at least J is the same as partitions such that mech J minus J is odd. Or it's also the same as partitions of n plus J, whose Frobenius symbol has no J in its top row. So somewhere hidden on these right-hand sides are more 5 cycles and 7 cycles. Not referring to any crank, but referring to this mech or this Frobenius notation. I don't know what that is. Okay, that's the end of the first part of today's talk. Any questions about the ranks and the cranks? No.
Dennis, you said you didn't want to go too much further, splitting out ones and then twos and then threes and then mores. Do you have any guesses? Do you think this could be done indefinitely with some sort of new thing resulting if you like take the limit as the split out terms? You know, you try all of them, and I think you might get some sort of unlimited construct there for a new statistic?
You know, I don't know about that. Already this was not the kind of thing that took me only one day to do. Even this case took me several days to figure out. So it's conceivable that if you have better insight than I do, you can do that, but I could not do that. It's actually not so hard because you just do a Q binomial theorem, but you have to combine terms together in clever ways to get positive terms. And the more terms you break off, the more clever you have to be. So with my limited cleverness, I couldn't go very far. But maybe you can. I don't know. And I don't know what the resulting thing would be if you let it go off to infinity. I just don't know.
Makes sense.
Okay, other questions? Okay, here's the second part of today's talk. These are the Rogers-Ramanujan identities. The top one is the first Rogers-Ramanujan, and the bottom one is the second. Notice the right-hand sides are 1 and 4 mod 5 or 2 and 3 mod 5. They're found by Rogers in 1894, and Ramanujan, he knew them before 1917, but that's when he had his proof. And Schur also, during World War I, knew these identities, independent of Rogers or Ramanujan. Now, in Math Reviews, I did this little search a couple of years ago. Found almost 1,000 papers, more than 200 in the last decade, 11 theses, and Drew has written a book about these identities. So it's a very active area of research. A few historical remarks for those of you who haven't seen this. Ramanujan, in his letter to Hardy, more or less tried to keep secret that he knew these identities. He sent him some corollaries of these identities, like these continued fractions here, which are pretty amazing, and they amount to changing Q to be a certain exponential and evaluating those infinite products. And Q is this exponential. And here's the continued fraction that Ramanujan did know but didn't tell Hardy. That this very natural continued fraction, which is the power is going down the diagonal here, has this quotient of infinite products is the answer. Now I'm going to show you a modern version of Rogers' 1894 proof. But before I show that, I want to just show you a slide which has many other directions for Rogers-Ramanujan, and some people's names are missing that's so huge I couldn't write in all the names. Let's just look at this slide. So I apologize. So there are lots of different proofs. There's Q-series proofs. There's a representation theory proof using affine Lie algebras. Conformal field theory proofs. I want to say Omar Foda's name here in particular. He, I'm afraid, passed away last May. He was a very nice fellow. There's some metric function proofs. There's a combinatorial proof of Garcia and Milne that was the beginning of what's called the involution principle, but it's not a direct proof. Computer algebra proofs, probability proofs, random matrices over a finite field, statistical mechanics proofs. There's more. There's a knot theory proofs. Let me show you what Rogers' proof is. Even though he never wrote it like this, this is what he was really doing in 1894. Let's take this integral I of t I have up here on top. Now there's one typo. This exponential should be negative xt plus t squared over 2. So what does this look like? It looks like you could just complete the square in x and do this integral. This is a very easy integral you could give to your calculus students, as long as it was correct. Here it's incorrect because there's a 2 missing, but that's okay. There's nothing hard about this. It's just a bunch of exponentials to do. We're going to write down a Q version of this. For the Q version, I'm going to replace this e to the minus x squared over 2 by a weight function. That's the weight function for the Q Hermite polynomials. That's this infinite product here. And this other exponential is the generating function for Hermite polynomials. I replace it by a certain Q inverse Hermite generating function. So this exponential goes to this generating function, this goes to this weight. And I now am going to take this integral and evaluate it in 2 different ways by using 2 kinds of orthogonalities. If I use Q Hermite orthogonality, I'll get this exact sum. I'll get the sum side of Rogers-Ramanujan. So there's some details here I'm leaving out. You just have to believe it's pretty routine to do this orthogonality. You'll get the sum. If you do Fourier orthogonality, in other words, these exponentials are orthogonal, you get the product side. And the reason you get the product side with mod 5 is there's a 1 theta here and a 2 theta there, and 1 squared plus 2 squared is 5. That's where the 5 comes from. Well, this is what Rogers was doing in 1894. He's basically doing a Q version of a very simple integral, evaluating it in 2 different ways and seeing what you get. You get the sum equals the product. Any questions about this? Well, but MacMahon gave the combinatorial interpretation in terms of partitions. So here's his interpretation. He said, number of partitions into n with difference at least 2 equals partitions of n into parts congruent to 1 or 4 mod 5. So here I took n equal to 10. Here are the parts that differ at least by 2. And here are the parts which are 1, 4, 6, or 9. The second one has no 1s in it. And then 2, 3, 7, 8. Now there are many generalizations of this. There's so many things I couldn't write, just a tiny sample. And there are many new type Rogers-Ramanujan identities. For example, there are these new ones due to Kanata and Russell that have recently been proven. This last proof of Rosengren uses the same idea as Rogers' original idea. Take an integral and evaluate it in 2 different ways. you'll get a sum side and a product side. So it's kind of humorous that 125 years later, we've come, in some sense, full circle. Well, right now today, there is no known Q-series proof with only positive terms and no cancellation. All of these proofs have some cancellation in them somewhere. And usually the cancellation comes from this fact right here, I've written in blue, that the 1 in 4 mod 5 comes from a Jacobi triple product divided by a Q infinity. The Jacobi triple product is 2, 3, 5, leaving 1 in 4 mod 5. There's no known proof, so there's no known direct bijection. This is still an open problem. Find a direct bijection. I would just like to find a Q-series proof with no cancellations, all positive terms. Then I'm pretty confident we could bijectify every step of that proof and come up with a straight bijection. I'll say more about that later. But for today's talk, I'm going to talk about some work I did with Kathy O'Hara, where we refine Rogers-Ramanujan. We do something stronger mod 5. We don't generalize it to other moduli. We do something stronger than Rogers-Ramanujan. And what I'll want to talk about is marking apart. For example, in Rogers-Ramanujan, if I say, I have partitions with 1 or 4 mod 5, but I have 38 copies of 11s. I tell you exactly how many 11s there are. What does that correspond to on the difference side? Of course, if we had a bijection, we would know what it does, but we don't have a bijection. So it's working toward a bijection. So here's an example of such a theorem. Take a part that's 0 or 4 mod 5 and take partitions into parts 1 or 4 mod 5 that have exactly k of those parts. What does it change into the difference side? Difference at least 2, and either you have 1 part and n over m equals k, or you have at least 2 parts and this difference of the first 2 parts is k. Does everyone understand that this is a refinement? Basically, what this means is if I were to take the Rogers-Ramanujan identities, these things right here, and where I had an m over here, I write a little x in front of the q, or I write an x. And then x has to appear over here somewhere in some complicated way. So we figured out how to do that. And the resulting combinatorial theorem is this theorem right here, hopefully. Oh, sorry about this. Is this theorem. Well, we did lots more. For example, we figured out, suppose I had the second Rogers-Ramanujan and I weight the 2's by a T, the 3's by a W, and the 7's by a V. Can I tell you what happens on the other side? The answer is yes. I can tell you combinatorially what happens. It's a little complicated because the identity is a little complicated. I'm going to show you the key identity in this case that will work. It says you take the TWV version and the first 7 terms of Rogers-Ramanujan, and you write it as the TWV version of 1 times a new 7 terms, which is this. What makes this work is that everything is positive. They're all positive terms everywhere. So if you interpret this combinatorially, you can write down a statement. Of course, if you had this for all values of the part size, you'd have a strict bijection. You'd completely solve the bijection problem, and you'd have a completely new identity. Now, we found these identities using the computer, but I really believe that they should come from commutative algebra. They look like Hilbert series for some kind of graded ring. So I'm really hoping that there'll be a commutative algebra proof of these types of rational function identities where everything is positive. Or they may be related to counting points in polytopes. But right now I have no good explanation for these identities, why they should exist. But they do seem to exist with positive coefficients. It's very surprising. Note, if t and w equal 1, this is 1 plus q over 1 minus q squared. This is 1 minus q. There's actually cancellation here, as there is here. There's cancellation there too. Plus, these identities are not unique. There's more than one of these, which makes them harder to find if they're not unique. So I don't understand this. Here is another example of such a theorem. Here's what happens if you take Rogers-Ramanujan mod 1 and 4 and replace the parts 1 and 4 by a 2 and a 3. So it's very strange. The parts instead of 1, 4, 6, 9, 11, 14, 16 are 2, 3, 6, 9, 11, 14, 16. It's kind of a mixture of the two theorems. What do you get for the different side? For the different side, it says difference at least 2. If you have a single part, then the single part can't be 1 mod 3. And if you have at least 2 parts, then this difference can't be 1 mod 3. It's nothing you would predict at all why that should be. But what comes out of the generating functions? We don't have a general theorem of having the first initial segment 2 and 3 and then the final segment 1 and 4. I don't know how to do that. Here's a fact. It's known that there are more Rogers-Ramanujan partitions with 1 and 4 than there are 2 and 3. And that's because when you take the difference of the sum sides, you can prove that's positive. Yeah, this can be generalized in the following way. Take a part or a partition theta, and let's just think of theta as a part size. And E super A of theta is a number of partitions of n that have theta k times. So this theorem says, take 2 possible sets of parts, 1 and 4 mod 5 or 2 and 3 mod 5. Take a partition of m that comes from A, like m equal to 9, and theta from m, like theta equals 7, 2. That is always true that the 2, 3, 7, 8s are less than or equal to the 1, 4, 6, 9s. So this is a refinement of this simple fact up here. It's always true. Okay, I have 10 minutes to go in the talk. I will end on time, don't worry. So now I'm going to talk about some questions and speculations. So this is dangerous in that most of us have tried to do Rogers-Ramanujan bijections and we've all failed. So I'm going to not to try to show you all my failings, but hopefully some interesting things. This first one is not a failing. It's a very neat thing. Look at this left-hand sum side. It's basically Rogers-Ramanujan sum side. The right side, notice there's a T here, is a basic hypergeometric series on base q to the 5th. Now notice Rogers-Ramanujan, all those infinite products are on base q to the 5th. Here's how you change it into base q to the 5th with a T. And a T were equal to 1 over q, this 3 feet 2 would have a 1 here. It would completely knock out and go away. You just get infinite products. You get Rogers-Ramanujan. The only known proof of this identity uses orthogonal polynomials. I don't know what this identity is in all those other possibilities for all those other areas of math. What is this saying? You would think that in the Lie algebra A11 that does Rogers-Ramanujan, this would have a lot of meaning. But I asked Jim Lepowski, he said he didn't know. Maybe one of you will know. This right-hand side is not manifestly positive. There's cancellation going there. I don't even know a Q-series proof of this. The only proof I know uses calculating an integral in 2 different ways. The integral is hidden here. The next speculation are, there are polynomial versions of Rogers-Ramanujan. Dave Berceau, Schur, and Drew has worked quite a lot on this. For example, A here is Dave Berceau's polynomial version. It says this, for any n, this polynomial in n on the left equals the polynomial in n on the right. And when you let n go to infinity, you get Rogers-Ramanujan. This goes to the sum side on the left, and using the Jacobi triple product, the right-hand side goes to the 1 or 4 mod 5s. Now we know what this left-hand side counts in terms of partitions. It's partitions difference to rank at most n minus 1. The same rank function. What is the right-hand side as a set of partitions 1 or 4 which are restricted by n in some way? I don't know the answer to this. It looks like it should be very easy to do by inclusion and exclusion. But I don't know how to do that. It's very frustrating. Now, if someone here at the talk knows how to do this, please speak up right now and tell me that yes, you can do this. Like, I'd really like to hear Drew tell me, yes, Drew, you know how to do this. Do you?
Sorry, I don't.
I wish you could. I wish I could, but I can't. Well, this is a very frustrating problem. It looks like it should be not hard at all. Here's another set of polynomials. These are due to Schur against a slightly different Q binomial coefficient. So this time, it's not the rank that's bounded by n, just the largest part is bounded by n. It's very simple. Partitions difference 2 with largest part at most n. And this right side, how does the n come into the partitions mod 1 or 4? We don't know. To make this even worse, these left-hand polynomials are Q Fibonacci numbers, have a very, very simple recurrence. All you need to do is to figure out what the 1 or 4 mod 5 partitions are that have this Q Fibonacci recurrence, and you'll be done. I couldn't do this. I'm admitting I'm not very good, but I tried. These look doable to me. Number 3, now I'm really getting speculative.
Oh, Dennis, just before you continue, we have a question in the chat about.
Oh, okay. Let's hear the question.
So William asks for slide 44, the request is to give a manifestly positive combinatorial interpretation for the identities on the right-hand side. Is
That's
that
right.
correct?
Absolutely. In terms of partitions 1 or 4 mod 5. We know what it is on the left-hand side. Since they're equal, we could say it's equal to the right, but we don't want that. We want 1 or 4 mod 5. Manifestly positive, no minuses.
Mhm.
And probably, you know, J equals 0, it should be a subset of this 2n choose n's, you know, in some complicated way. I don't know that. Any other questions on slide 44?
Nope, I think that was it.
Okay. Now here's a third speculation. Let's take the 1 or 4 mod 5, and instead of doing Rogers-Ramanujan with 1 minus q up to 1 minus q to the m, let's put 1 minus q to the 5 up to 1 minus q to the 5m. Because after all, parts on this left side, this product side, change by 5s. Make the 5s over here. How does it change? Well, this get a new polynomial, which is just this quotient, 1 minus q to the 5 up to 1 minus q to the 5m over 1 minus q up to 1 minus q to the m. There's 5 to the m partitions in there. We know what they mean with difference 2. They just tell you the multiplicities of the columns. What the multiplicities of the columns are, mod 0, 1, 2, 3, and 4. We'd like to realize these 5 to the m partitions in terms of 1s and 4 mod 5s. Then we can match them over here, and we'd have a bijection. Don't know how to do that. In particular, it looks like this is true. It'd be an XY version of Rogers-Ramanujan. Weight all the 1 mod 5s by x's and the 4 mod 5s by y's. I think that there is a positive polynomial here in q, x, and y that makes this true. So there should be some xy weighting on these 5 to the m partitions of 1 and 4 that give this polynomial. Trouble is this polynomial is not unique. I started finding these polynomials. You can find them. Okay, in the 1 or 2 minutes I have left, I'll have my final amazing fact on Rogers-Ramanujan. Let's take the Rogers-Ramanujan numbers 1, 4, 6, 9, 11, 14, etc. Let's write them as a sequence, A1, A2, A3. Look at this fact. If I multiply them together, the first m of them, and divide by m factorial, it's an integer except for the 5s. After all the numbers in the top are not 0 mod 5, and the numbers in the bottom do have some 0 mod 5s. We know what this 5 is. It's the 5-adic part of m factorial. We know what that is. So this is a fact that's true. In fact, it's true for primes. Take integers that are plus or minus I mod p, do the same quotient, you always get an integer over p to the e. Well, this was a little surprising to me when I thought about this, because after all, what we're trying to do in a bijection is to change factors like this in the sum side into factors like this on the product side. So for example, if I do this for 4, I change 1, 2, 3, 4, these 4 factors into 1, 4, 6, 9 at the expense of this numerator polynomial. That numerator polynomial is closely related to this numerator integer. This numerator polynomial you can interpret for small values of m as partitions with parts 1, 4 mod 5. So that begins to give a Rogers-Ramanujan bijection. So with Kathy O'Hare, I worked this up to the first 7 terms in the sum side of Rogers-Ramanujan. So I'm afraid that this numerator polynomial had hundreds of terms in it. It got to be a little complicated. I was hoping some magic like lightning bolts from the sky would show up to tell us what to do in general, but they did not. But maybe if you understood this question better than I do, like what this integer counts in terms of partitions, you'd have a better answer. Well, my time has elapsed. You can find many of these questions on my webpage. Thank you very much.
Okay, well, thank you, Dennis. So I think, well, if people want to, there's a button you can use for the clapping if people want to virtually clap. I see some of you have found it. So I'll ask people now then if they have any questions. So feel free to unmute yourself or type it in the comments.
I'm afraid I don't see these comments.
I'll
Can you relay them to me, Larry?
Yep.
Well, if no one's going to ask, I'll ask. Can you go back to the with the early slide? You're showing the arithmetic progressions in the dihedral groups.
Yes.
I computed a few numbers out. I just wanted to compare and see if they matched up. If that's the only.
This slide.
Yeah.
Mm-hmm.
Let's see. 4 it all matches up.
Do you have a way of predicting what these dihedral groups are, perhaps?
Yes, I do. Well, the actual numbers of the dihedral groups, I'm not so sure, but I can tell you when they match up. So, for example, 7n plus 1, 7n plus 3, and 7n plus 4 match up. I can predict that for you.
Are they quadratic residues or something else?
No, they're orbits in a Ramanujan-Kohlberg identity.
Yes.
When you try to set up an identity, say you take the arithmetic progression for p of, say, 7n plus 1, you can try and build this into a modular function. And what happens is that generating function will send 7n plus 1 to 7n plus 3. And then it will send that to 7n plus 4, and then it'll send that back to 7n plus 1. So you have an orbit. You build a modular function around that.
Okay.
So now, as for the actual size of the dihedral groups, I couldn't tell you right off the bat. I probably have to think about it.
You know, we're highly interested in this 5 cycle and this 7 cycle. In some
Might
sense, that's why those Ramanujan congruences hold.
Might have to do with the congruent subgroup you're working over, at least for 7n plus 5 and 5n plus 4. 5 and 7, they're the congruent subgroups you're working over. But I couldn't tell you what the rest are. At least not right off the top of my head, and that's only a guess. Like actually figuring out why would be interesting.
Nick, are these Kohlberg identities, are they like general for like P of Tn plus R, or is it just certain residue classes?
You can do it for any of them in principle. I've gone up to 10. When there are complications once you get to 11 and on higher. Like for example, we have one for P of 11 and plus 6, but it's terrible. But yeah, in principle, you can get them for any arithmetic progressions. The question is how big they get on the left-hand side. So the nice ones are P of 5n plus 4 and P of 7n plus 5, because you only have the one series and you get the nice congruences out. But yeah, there's for P of 2n plus 1, P of 3n, P of 4n, P of 6n. It's just computing the right-hand side gets more difficult.
So what is it that's special about the Ramanujan-Kohlberg ones that shows when the dihedral groups should be the same size?
So what happens is you have, so for example, maybe go to the 5n's, they're a little smaller, right? So 5n plus 1 and 5n plus 2 match up there, you see, because it's D4. And then 5n and 5n plus 3 match up. So I can show you there are 3 Ramanujan-Kohlberg type identities. One of these identities, the left-hand side, is just P of 5n plus 4. That's the classic one that everyone knows about, his really beautiful identity. there's another identity that has the generating function for P of 5n plus 1, and it's that infinite sum, multiplied by the sum P of 5n plus 2. So those two series are multiplied together on the left-hand side. And there's a third one, P of 5n, that infinite series, multiplied by P of 5n plus 3, those series. So the dihedral groups, whenever they match up here, they indicate a Ramanujan-Kohlberg identity. And they tell you which arithmetic progressions are going to be on the left-hand side. Like this, at least by inspection, it works. For all the way up to and it also tells you, for example, P of 6n plus j, they all match. That's because if you look at the Ramanujan-Kohlberg identity, it's just all 6 series multiplied together on the left-hand side. There's a single identity. Same thing with 3n plus j. You'll notice Z2. It's all matching up. It's P of 3n, P of 3n plus 1, P of 3n plus 2. All 3 series are multiplied on the left-hand side. They don't break up into different identities. It's one single identity. I can compute them out for most of them. P of 6n plus j would be hard because the congruent subgroup is enormous. The others are doable.
I see. Interesting. Josh Males also has a comment. He says that for the 7-core case, he has a recent paper that's now on archive with Katrin Brigman and Ben Kane on how to build quadratic forms associated to them following Ono and Z. So I think this is an older paper of Ono and Lawrence Z, maybe on the 4 cores and their relation to class numbers. Anyway, so Josh suggests that this new paper that he has on the 7 cores is perhaps useful in studying, if you look at those in more detail, something related to this.
Will he be able to predict these dihedral groups?
Josh, if you want to turn your microphone off.
Yeah, sorry, I didn't want to interrupt before. I'm not sure whether we'll be able to predict the dihedral groups directly. So we were concentrating on just self-conjugate 7 cores.
Yeah.
For this paper. But of course, the way to build all of these 7-core partitions is exactly the same if we're not looking at self-conjugate. And it feels to me like there should be a natural way to expect dihedral groups to show up. But I'll have to think about it some more. I couldn't say yes or no directly.
So Josh, you did 7, but are other primes, or I guess not even prime, other numbers are also, there's like a procedure for producing this kind of stuff?
Yeah, you just follow these abaci and extended T residue diagrams to build these quadratic forms.
Well, in some sense, that's what we did to get to this generating function here.
Right, yeah. But perhaps there's a way to, well, especially in the self-conjugate 7-core case is particularly related to genera in class groups. And of course, you can exploit some of the symmetries and sizes of genera in class groups. So that's what we did with self-conjugate 7 cores. But perhaps there's a natural way in which the non-self-conjugate cores also split up into genera and class groups, things like this.
Yeah, good idea.
All right. Any further questions, I guess? It doesn't look like it. So Larry and I planned that the Zoom can go until